Howdy, and welcome once more to Math 153, Elementary Statistics. I am Lance Curtis, and this is the lecture for sections 2.3 and 2.4. Section 2.3 is all about histograms, so let's jump on in. A histogram is simply nothing more than the graphical form of a frequency distribution. Notice the shape of the distribution for the histogram at right. If we report, instead of counts, we report percentages, then we get a relative frequency histogram. Now, observe that the general shape of the distribution remained essentially the same. So, it doesn't matter whether or not you report counts or percents when making your histogram as far as the shape of the distribution is concerned. The shape of the distribution will not change essentially. However, if you want to change the shape of the distribution, you will see that if you change the number of bins or classes or categories into which you put your data. We're not making these because they're cute, okay? We want to understand the data better, and that's what a histogram enables us to do. Typically, in looking at the shape of the distribution, we want to see the data assume what's called a normal distribution, okay? There are many statistical analysis methods that require data to have a normal distribution. So in order to use these tools that are in our toolbox, we first have to ascertain, is the data normally distributed? Recall that a normal distribution has the characteristic bell shape, and that it's essentially symmetrical, which means each half of the graph mirrors the other. If we look at the normal distribution there on the right and compare it with the shape of our histogram there on the left, we can see that we are roughly the same. Okay, now it's not identical. Okay, don't get so caught up in detail when you're asked, does this look like it's roughly approximating a normal distribution? Some students like to say, well, there's a little bit over here, but there's a lot more data over here, so it's not exactly symmetrical. Just ignore that. What you're looking for is the bulk of the data right around the middle. It's got that rough characteristic data shape. Low values here, low values here, when compared with the high values in the center of the curve. This approximates a rough normal distribution. So if I were asked, does this approximate a normal distribution? Just by eyesight, I would say, well, it appears so. Of course, there are tests that we can run to ascertain that. One of the things that we look at when trying to ascertain normality is skewness. Okay, so a distribution and the data underlying it can be skewed, okay, if it's not symmetrical. So the curve in the center is your standard normal distribution curve, perfectly symmetrical around its center. There is no skew with this curve. However, if the data were to shift to the right or to the left, then we get the curves that are shown on the ends of the graphic at the bottom of the slide. Now, here's a point where a lot of students can get confused. And I don't blame them because I get confused too. When I was in industry, we always looked at it and said, okay, so if the data is going to be over on the right side of the graph, see how all the data shifted towards the right, then we would call that a right skewed distribution. Similarly, if all the data shifts over to the left, we would call that a left skewed distribution. Statisticians don't always think in such a straightforward manner, okay? They think backwards sometimes, and some people would argue that it's more than sometimes. Here's a case in point. To a statistician, they're not looking at where the bulk of the data is, even though they say the data is skewed in a particular direction. They're looking at the longer tail that's being created when you shift the data. So, because the longer tail in this distribution here on the left is over on the left side of the graph, they're saying that the data is skewed negatively. It's skewed to the left because it has a longer left tail. Conversely, if you shift all the data to the left, you get a longer tail on the right, so then they would say that the data is skewed to the right, or it's positively skewed because it has a longer tail on the right, or a longer tail in the positive direction. Now, keep in mind, these are only conventions. Okay? There's nothing to say that the way I was doing it in industry was more right or more wrong than the way statisticians doing it. And conversely, there's nothing to say that the statisticians were more right or wrong than my work companions in industry. There's a convention that's adopted, okay? So when it comes to doing your homework and your quizzes, use the statistician's convention, okay? Focus on where the tail is, because you will get questions that ask you about, is the data skewed? And if so, is it positive or negative? Is it skewed to the right or is it skewed to the left? So just use the statistician's convention and you'll do okay with the homework and the quizzes and the tests. Even though, from my standpoint, it makes much more sense to say, look, if you're going to talk about where the data is skewed, then look at where it is on the graph. I mean, that just makes sense to me. That just seems straightforward. But again, I'm not a statistician. I'm an engineer. Okay. Statisticians, as I said, don't always think the way you and I think. Sometimes they think backwards. I mentioned before, there are ways in which we can assess normality other than just looking at the graph. Okay, looking at the graph gives us a rough approximation, but it's not exactly statistically sound. So what we're going to do is we're going to use what's called a normal quantile plot. Okay, normal quantile plots are also called normal probability plots. It is a special type of what's called a QQ probability plot. A QQ probability plot is simply a statistical graph that lets us know how well does our data match a given distribution. So if we want to know how well our data matches a normal distribution, then the QQ probability plot becomes called a normal quantile plot or normal probability plot. So you can see there on the left the histogram with the normal distribution superimposed upon it. There on the right, the normal quantile plot. This data in the histogram actually represents fairly well a normal distribution. Notice how the data points are really close to that line of best fit. That's what you want to see. Notice also that the line of best fit goes from left to right. That's always going to be there. If the line ever goes the other way, okay, in other words, if the line has a negative slope, then something's wrong with the way the plot was constructed. You need to go back and figure it out. The test and the graph are designed so that you always have a positive slope with that line of best fit. Typically, you don't have to worry about that because we have software here in the 21st century that does everything for us. So we just give it our data set, tell it to go make our plot, and then we can look at it and evaluate. In the old school days, you would have to do all of this by hand. And there was actually special normal probability plot paper that you would need in order to draw one of these graphs. It was a time-consuming and laborious process. Oh, I'm so thankful, and you're going to be thankful too, that we live in the 21st century. So how do we interpret this? As I said, you want the data points to lie as close as possible to that line of best fit. That's what indicates normality. Okay? Sometimes you're going to see plots that don't indicate that. So for example, here you have lots of data points that are far removed from the line of best fit. So this is going to indicate there's some sort of skewness in the data. Not exactly normal distribution. Okay? Here on the other side, okay, we have the data points fairly close to the line of best fit, but look how they make a pattern around the line. So here they're dipping down below, then they come back and they go above, then they dip back below again, then they come back above again. So this sort of sinusoidal pattern around the line of best fit indicates a lack of normality. Usually it indicates that you've got some sort of distribution of the data concentrated way too much in the center. In both of these cases, we have a lack of normality, in which case some of the tools that we're going to learn about later in our toolbox we won't be able to use on these distributions. We'll have to fit them to another distribution, okay? Which means going back and making another QQ plot. Now, there are statistical programs that you can just give it the data set And it's already programmed with all the algorithms so that it tests each one of the possible distributions, and then it'll rank them. The statistical software package that I was using in industry was called Weibull++, would do that for your data. Okay, you give it the data set, you put it in, you say, hey, find me my distribution, and then it ranks them according to how well they best fit, and then you get to decide, okay, which one of these is actually the one that we're going to be using for our analysis. So you don't have to do all of the stuff by hand. Again, it's very good that we're living in the 21st century. Okay? As I said, if the line of best fit doesn't go up from left to right, if it doesn't have a positive slope, then there's something wrong with the graph. Okay? Typically, you're not going to have to worry about that because, as I said, computer software will generate the plot for you. So that's a basic rundown on histograms. Let's dive down into the last section in Chapter 2, which talks about graphs. Graphs communicate information about the data, but sometimes the way we present that information can be deceptive. So histograms are one way in which we can organize statistical data and present it to other people. However, there are many other choices, and we're going to talk about those choices here in this section. Some are more effective, some are less effective. But remember, the point of making a visual representation of your data is to communicate important characteristics of your data set. So you want to choose the graph that best communicates those important characteristics of your data set. Okay? The way you set up your graph, okay, although it may convey information which is technically correct, the way in which it conveys that information can be deceptive. So first, let's talk about the different types of ways we can represent the data, and then we'll end this section and also the lecture with a brief conversation about ways in which we can use data to make less than effective representations of the important characteristics we're trying to communicate. So first up, we have scatter plots. Now, a scatter plot is one of the most common graphs that's made. So typically, when you're looking at statistical analysis, one of the first plots you always make is a scatter plot. There's so much information that you can get from the scatter plot. Okay, so for example, if I'm looking at this scatter plot here, okay, it's showing me the relationship between the two variables in my data set. In this case, number of users and memory. Okay, apparently it was someone who took statistical data on the amount of memory that was being used and the number of users that were on a particular network. Notice the relatively straight line that we get when we plot the data in a scatter point. This tells me that one of my next steps is going to be, okay, let's do a linear regression model, which we'll learn about later in the course. Without making the scatter plot first, then I might be wasting my time with the linear regression model. There might be another model that I need to make that would be a better fit for the data. So scatter plot's always good to know because it tells us what's our next step in order to be most effective and efficient with our time. Here's another example of a scatter plot, what we call a shotgun effect, because it looks like someone took their shotgun and fired it out at the target on the wall. Data points are skewed all over the place. So if I see this type of arrangement on a scatter plot, I'm going to know, hey, if I try to make that linear regression model, I'm not going to get a very good fit. In fact, something like this tells me there's not a whole lot of relationship between price and quality, which are the two variables in this data set. That being said, I now know that I need to look for another type of distribution, or perhaps there's another way to relate the two variables between price and quality. Perhaps there are some confounding variables not found in my data set, and I need to go look at some of those and include them as appropriate. Time series graph will show data collected from different points in time. So here we have an example of timber production for quarters of the year. So for each quarter, there's a data point. The graph can go up and down. You typically see these types of graphs also with, say, stock markets. So you'll have investment companies that will produce graphs that show, over time, things like the Dow Jones Industrial Average. You're just collecting data at different points in time and plotting it on the chart, and it just goes up and down. Dot plots. Dot plots are basically a graph in which you take each data value in your set and plot it as a dot along a scale. Okay? So for the table that we see here on the left, okay, here are all the possible data values in the data set, and then we count how many of those values are in the data set. So our data set contains no zeros. There's 1 1 in the data set. There's 1 2 in the data set. There's no 3s in the data set. There are 2 4s, 6 5s, so on and so forth. So notice how there's no zeros. There's 1 1, 1 2, no 3s, 2 4s, 1 2 3 4 5 6 5s, so on and so forth. We're representing equal values by stacking the dots over each other. Okay? This gives the graph the appearance of a histogram, even though technically it's not. There are applications in which sometimes a dot plot can be very helpful, but again, a lot of the ways in which data is graphically presented or visually represented is simply a matter of convention. So wherever it is that you end up working, there will be a convention for how we're going to display the data, and in some quarters, dot plots are the convention. In other cases, a stem plot is the convention. Stem plots are also known as stem and leaf plots, okay, because what you have is a stem and leaves. So here in the stem and leaf plot, I have a value of 10. So the 10, the 1 from the 10's place, the 0 from the 1's place, I have 13, and I have 16. So 10, 13, and 16 all share that 1 in the 10's place. So that 1 becomes our stem, and the leaves of that stem, branching out, are the 0, the 3, and the 6. Likewise here I have 21, 26, 27, 28. Notice how I have two 35s, 35, 35, then 36. There's two 41s, 41 and 41, so on and so forth. So the stem is the leftmost digit, and the leaf is the rightmost digit. So I'm reading this individual value here, okay, the 6 with the 1, that makes 16, okay. Again, we're stacking these just as we did in the dot plots, 35 and 35. Bar graphs. Most people are pretty familiar with bar graphs. It's simply a histogram for categorical or qualitative data. So here we have, what kind of pet do you own? And I love this graph because most of the people in the sample own cats. In fact, there are more people that own cats than dogs. I really like this graph because I'm a total cat person. It's once been said to me that I hate dogs, and I don't hate dogs. I just think cats are better. Here we have what's called a multiple bar graph down at the bottom of the slide. So we can actually take more than one bar graph, put them all on the same chart. That makes it a multiple bar graph. These are useful for comparing two or more data sets. And typically the different data sets will represent different groups in a statistical study. So here we have different groups, young males, young females, and senior citizens, all asked, what's your favorite milk drink flavor? I don't know what vanilla is. I guess that's regular milk. Yeah, I don't know. Actually, you know what? Some companies actually do make vanilla flavored milk. Yeah, okay. Anyway, so chocolate, vanilla, and strawberry, you can see the data results there. Pareto charts. Okay, I love Pareto charts. As an engineer, I can't tell you how many Pareto charts I've made. A Pareto chart is like a histogram, okay? But instead of arranging them in order of the categories or classes or bin values at the bottom of the graph, you're going to organize this by the counts or the relative frequency that each bar represents. So the largest bar goes on the left, and then you just count down from there in descending order. Okay, Pareto charts are great. Okay, they're based on the Pareto principle, also known as the 80-20 rule, which says 20% of your efforts produce 80% of your results. It comes from observations that were first published by an Italian economist in 1896. His name was Vilfredo Pareto. And what he noticed is that 20% of the population in Italy owned 80% of the land. He also noticed that 20% of the pea pods in his garden produced 80% of the peas. This 80-20 rule has been observed in many, many different scenarios. Okay? So, for example, 20% of the population is probably going to produce 80% of the accidents that we see out on the highway. 20% of your customers, if you're in business, 20% of your customers are typically going to provide you with 80% of your profits. Okay, most businesses have a few core clients that produce the bulk of their profits. So we see this in many different areas. As an engineer, I saw this frequently working with failure modes. So, for example, the chart here up at the top, here someone's looking at cost centers and say, so what's costing us the most money? What are we spending our money on? And so we make a Pareto chart and we say, okay, here are all the different costs, and we arrange them in descending order from greatest to smallest. Typically, when you do this, if you have a significant number of bins, okay, you're going to see a plateau somewhere towards the center of your graph. And the plateau, which I would say would be right about here, is going to separate what we call signal, which is the really big stuff that you want to communicate, from the noise, which is the stuff you just need to avoid. Just don't even pay attention to it. Ignore it. So here in this Pareto chart for cost center, if you want to reduce your costs, the first thing you need to tackle is, let's look at our parts and materials. And then let's look at our manufacturing equipment. Let's tackle these two items. Because typically what you have in industry or any business enterprise is a limited amount of resources, limited amount of time, limited amount of money, limited amount of personnel or manpower. Now, working as I was for a Fortune 500 company that, was internationally based and had billions of dollars in cash flow, you would think that I wouldn't need to go through a procedure like this. However, it's a large international organization. There are lots of people who have plans for those billions of dollars in cash flow. So the amount that you're actually going to get is going to be limited. Furthermore, the people that are actually going to have the time available to do the work of looking into this is going to be limited as well. So the question becomes, how do we get the most bang for our buck? How do we make the best use of our resources when those resources are limited? And the Pareto chart is a great way to answer that question, because it can key you in on these are the biggest items that you have, and you need to figure out, okay, what can we do about this? So in this specific example, you're looking at costs. You want to reduce your costs. So is there a way that we can reduce costs on parts and materials? Perhaps we can provide more parts so we can get them cheaper. Okay. Or conversely, perhaps it would be better if we spend a little more money on a part that actually lasted longer, because then we wouldn't need to replace it as often. So you obviously would need to do studies on the different options available to you to figure out which is the best way to go. But that's the point of the Pareto chart. It points you in the right direction so that you can know, how do we get the most bang for our buck? How do we use limited resources to best effect? Pie charts. Lots of people are familiar with pie charts. They basically take qualitative data and they put it in a circle, pieces of pie. So each piece of the pie is a different size because it represents a different proportion to the whole. Pie charts can be based on frequency counts, or they can be based on relative frequency, which in percents, which is typically how they're presented. Frequency polygons. These are essentially histograms without the bars. So because we don't have bars, the graph is represented with simply a straight line. So as you can see here, we have straight lines connecting the center of each of the bars in a histogram. And then this line becomes the graph itself. This is a frequency polygon. Here we have an example of a frequency polygon for test scores. So, number of students who scored in each bin is recorded here, And we can see the representation of our data here. What frequency polygons are really useful for is emphasizing differences between the counts or relative percentages that are in each of the bins. You can sort of see that with the whole histogram, but taking away the bars highlights those differences even more. And so looking at the change in slope between each of my data points here gives me an indication of the differences between the two bins. Sometimes that's advantageous to look at. Ogives. An ogive is simply a line graph that depicts a cumulative frequency. So, kind of like the frequency polygon that we were looking at just a moment ago, instead of looking at each individual data point, so where the line goes up and down, now the line is going to continually go up. Ogives are really useful for letting us know what portion of the data set is in which part of the data set. So here I can see, in this particular example, we're looking at an ogive for glucose blood level after fasting. Okay, the bulk of my data, which is the area underneath the, represented by the area underneath the curve, is over here at the end. Okay, that tells me glucose blood level after fasting. Okay, the bulk of my data is going to be over here on this side of the graph. Ogives can be really helpful, especially if you're looking at a scale of values and you want to know how does a variable or an effect change on that scale. So if we were looking at, say, blood glucose levels as our scale here, then this tells me that there's a pretty gradual change from low blood level to high blood level of glucose. That's probably a good thing. You don't want your blood to shoot up with glucose level in a really rapid rate, because that would probably wreak havoc on your body. So those are different types of graphs. Now let's take a look at some of the ways in which graphs can be deceptive or misleading. One of the common ways we see is with a graph that does not have a zero axis displayed. What this does is it exaggerates the differences between the elements that you're comparing. So take, for example, 3 models of automobiles shown here in the histogram on the bottom. We're looking at highway fuel consumption in miles per gallon. Now, admittedly, look at the values for each of these models. So Honda Civic on average 36, Chevy Aveo 34, Toyota Camry 31. Really not that much difference between 34 and 36, and yet the way this graph is displayed, you would think, wow, it's pretty substantial, because this is a significant part of the whole bar. So because we don't have that 0 that we're starting out with, here we're starting out at 28 instead, this graph serves to exaggerate the differences between the 3 car models, even though the differences are not all that great. If we wanted to make a more quote-unquote truthful graph, we would have a 0 point. So when we graph with a 0 point, now here, look, see, the differences are not all that much, which is what we get when we actually compare the numerical values represented behind the graph. So while this graph is technically correct, it's not lying about where the bars are ending up at the top. Because there's no bottom, the graph is actually exaggerating the differences between these 3 models of cars, when in actuality, there really isn't all that much difference. So make sure that when you're looking at a bar graph like this, you start out with 0. Because if you're not starting out with 0, it tends to be that the differences between a model would be exaggerating. So something like this you might see in an advertisement for a Honda Civic, because Honda wants you to buy their car and not the car from their competitors. Pictographs are also often used to represent data, but they can also create false and distorted impressions of the data if they're not used appropriately. One of the main reasons for this is because pictographs tend to use areas and volumes. It becomes misleading because if you double each side of a square, you don't double the area of the square. What you're doing is you're increasing the area by a factor of 4, because area is length times width. So you're going to take each of those sides, 2 times 2, and the area increases by a factor of 4. Likewise, with a cube, volume doesn't merely double just because you double each side of a cube. If you double each side of a cube, your volume has increased by a factor of 8. 2 times 2 times 2. So, because of this effect, pictographs that use areas and volumes can be especially misleading. Look at the pictograph here. So you're looking at trash. And I don't know if this is trash usage or if this is trash that was disposed, but clearly there's an increase from 1960 to 1980 to 2000. But is the increase really all that much? We don't really know. The pictograph would seem to suggest that it is, because this trash can for 2000 is much larger than this trash can for 1980, which is much larger than this trash can for 1960. But where exactly are we marking the value? Is it here towards the top of the can? Is it here towards the top of the lid? I mean, if we use the top of the lid, then the values are 100, which goes to 175, which goes to 250. So maybe not that exorbitant of a difference when we look at the numerical values. But again, we don't know that those are the numerical values. Perhaps they're here towards the center of the can. So maybe this is 50, maybe this is 100, and maybe this is 150. In which case the differences are even less. So the pictograph is actually misrepresenting the data. And with something like this, where you have only 3 categories, so you have a low number of categories that you're comparing, it's best to just give us a table with the numbers in it. I know the pictures look cute, but what we really want to do is communicate information effectively. And in this case, that's better done with a table. So if we just make a table that says, these are the years, these are the values, we can look at this and say, okay, that's really what it is. Now, of course, if you have an agenda that's served by creating an impression that there's a lot more trash in 2000 than there was 40 years earlier, then you would probably want to go with this type of representation. But again, it's not completely truthful. It's somewhat misleading because the differences are not that great. If you don't know the name Edward Tufte, he's very popular in the area of visual representation. He's considered one of the leaders of the field, especially when it regards to representing technical data. So if you want to know about how to make better presentations, more effective presentations, Edward Tufte is a good guy to look into. If you do look into Edward Tufte, you're going to find that he is often quoted as hating PowerPoint. There are reasons for that. Okay, when you have a PowerPoint presentation, all you do is click slides, then what you're doing is you're giving the power and authority in the room to the presentation slides. And he makes a good point. That being said, from my background in industry, everybody uses PowerPoint presentations. And oftentimes, PowerPoint presentations become the documentation for the real world work that's being done. So there's no way to get away from PowerPoint presentations, especially when many of the people that are in some of the meetings that you're in are not in the same room. So in order for us to be looking at the same thing, we basically broadcast a PowerPoint presentation. So everyone's looking at, their computer screen and they're talking to each other on the phone. That's typically the way a lot of my meetings in industry went. I would try to avoid that if at all possible. If all of my people that I needed to meet with were in the same geographical location, I would get us all together in the same room so that we could look at each other. And it made such a difference. We didn't need the PowerPoint. We just needed a few charts and graphs that showed us the data behind what it is that we were looking at, so that then we can make the proper discussions and decisions to move forward. But if you haven't looked at Edward Tufte's work, give it a go. The Visual Display of Quantitative Information is a self-published book that he wrote, one of the most successful self-published books in history. contains a lot of really good recommendations. I have a few of them listed here on the slide. So as we saw previously, if you have a small data set, use a table instead of a graph. It's much more effective. A graph of a data should make the viewer focus on the true nature of the data, okay, not on other elements. So as we saw with the pictograph of the trash cans, okay, it's eye-catching with the graphics, but you're actually throwing people off from the actual data that you're trying to represent. And as we saw, we couldn't tell exactly what the data was. I mean, where are the measurement points there? So that's an example of a less effective presentation. Do not distort the data. Construct a graph to reveal the true nature of the data. So don't use a non-zero axis, for example, on your bar charts. Always make sure that you have a zero axis, because a non-zero axis will tend to distort, exaggerate the differences between your categories. Almost all the indicator graphs should be used for the data, not for the design elements. Again, he's focusing on the information you're trying to convey and not the packaging. And too often people focus too much on the packaging and not the actual information. So that's all we have for this lecture. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in class, and thank you for watching.